Hi guys, so after you guys have worked with some elimination substitution, now we get into some word problems before we move on to the next section. So I created about two or three word problems that, you might see a resemblance when you guys take your final exam in the chapter 5 test. So be sure you guys know how to do it. So let's go work with the first problem. This is a mixture type problem, which is very common. You have a vintner that fortifies his wine that contains 10% alcohol by adding 70% solution to it. The resulting mixture has an alcoholic strength of 16% and fills 1,001 liter bottles. How many liters L of the wine and the alcohol solution does the vintner use? We need to somehow construct a system of equation regarding this word problem right here. And when we're thinking about it, I recommend before you go for it is that you draw a picture. You draw a picture of what it's asking. We have a wine that contains 10% of alcohol. So let's already start off by drawing a wine bottle. Oops. So I might not be the best artist, but I will give it a shot. That looks terrible. That looks better. And then you have a wine bottle over here, whatever. Actually, I'm never gonna color it. I'm just gonna leave it like this. Well, we have a wine bottle, and then we're adding a 70% alcohol solution to it. So whatever bottle or container I have, it has 70% alcohol to it. This guy has 70% alcohol to it. And I'm pouring both of these bottles into a resulting container slash bottle that has. Let's see. I don't like the way they look. Let's draw it like this. Boom. I'm pouring it into a resulting bottle that has 16% alcohol strength. The goal of this word problem is that the vintner wants to strengthen their wine. It has 10% alcohol. This is 10% alcohol. And then we're adding a 70% solution. I don't know what that could be. It could be a 70% alcohol bottle. I don't know. I'm not going to go into too much detail about it. But we want to kind of combine these two. That way I can come up with a solution that has 16% strength. I want to strengthen that wine. Now, other information we know that this wine bottle or this final solution that I have, this bottle, is going to be 1,000 liters. So, how can we set up an equation out of this? Well, before we even set up equations, we have to understand that each equation that we set up has to relate to some sort of topic. Clearly, the system is about, the mixtures themselves, so that's not, part of the question. But what's a key underlying issue that we have been working with is alcohol percentages. So, one of my equations that I work out is going to be relating to alcohol percentages. Alcohol persist or alcohol amount. Let's say alcohol amount. All right. Another one that I have that's related, the only other tool I have possible in this word problem is this 1,000 liter bottle. So outside of alcohol amount, we also have volume. All right. So let's work with volume real quick. Do I have the volume amount of any single one of these containers? If you notice, I only have the volume of one container. The resulting mixture. So I do not know the volume for wine, so I'm gonna leave it as W. I don't know how much volume W has, and I do not know how much volume the green bottle has, which is our solution. So let's just say plus S. But I do know the volume of the resulting mixture, which I'm gonna put 1,000 liters. So I have one equation already set up. Great. Now, this equation has two variables, two unknowns at the moment. So now, let's talk about the percentages of alcohol. We need to know the alcohol amount, which we need to know about the percentages. How much alcohol percent does the wine carry? Well, it contains 0.10. 10% is 0.1. Oh, I'm sorry. 0.1 times the W. Right? And then how much percentages does the solution contain? Well, that's just 0.7S. Now, the last part is how much alcohol amount does the final bottle contain? It's 16%. And I already know how much amount I have in my bottle, so I should know how much alcohol content I actually have. I don't have to write it as percentages. This is all times 1,000. Percentages is just a representation. So I have this linear system right here. This linear system with two equations and two unknown. And I can simplify that, of course. I can simplify this into 0.10W plus 0.7S equals 160. W plus S equals 1,000. Now it's a matter of, hey, can I solve this guy out? Well, how can you solve it? You can do substitution or elimination. Now, for your purposes, I hope that you get more practice with elimination rather than substitution. And the reason why I say that is if you work with elimination, you get practice on both the elimination and the substitution. If you work on substitution, you don't get the elimination practice. We will be talking about elimination later on, and I'm going to be expecting you guys to have a complete mastery of it. So, what I can do here is to eliminate, I'm going to multiply this top equation by -10. Because I want to eliminate the wine bottle first. If I do so, I have -W minus 7S equals -1600. And then W plus S equals 1,000. And I'm hoping that you guys tried this out. Now you can add these together. This eliminates, so I have -6S equals -600, which S is equal to, what is that, 100? So that means this guy has 100 liters. Well, if I figure that out, remember, they have to add up to 100. So if I plug in S over here, I should instantly get the wine being, how much liters? 900 liters. Now, it's very important when you're doing these word problems, you answer the problem. I'm not going to write down 900, 100 to answer the word problem. That makes no sense at all. Algebraically, it does make sense, but I'm talking about a word problem. If you're introducing this to, some coworkers or whatever, and you had to solve this problem, you're not going to just give them an ordered pair. You're going to say, well, the solution, the 70% solution has 100 liters that I poured in, and the wine bottle that I poured in was 900 liters. So if you want to understand the context of this problem, to create this new mixture, this new solution that strengthens wine, I'm pouring in 900 liter of my wine and then only 100 liter of the 70% alcohol solution. And then that'll create that 16% strength of wine. So, to answer the question, we're going to say 900 liters of wine and 100 liters of 70% solution. So, that's the first type of word problem that we need to be able to answer. These mixture types. Now we go into another one that I find very interesting. Now, when I was looking through your textbooks, it doesn't really talk about this type of word problem, but I think it should be a staple. I think it should be a staple. So, Johnny has only quarters and nickels in his coin jar. If the coin jar totals $48.40, how many quarters and nickels are in the jar? Assume there are a total of 400 coins in the jar. So, we're going to create some equations with this, but we got to know our topics of our equation. What contents are they going to be relating to? Clearly, they're going to be relating to money in general, but we need to know specific categories, like we did over here. Over here was alcohol strength and volume. So if I highlight the key parts, we have in particular $48, 400 coins, and then you also have nickels and quarters. So I'll give you guys some time to think about that. You guys can pause the video, and then we will talk about it. All right, if you have written it down, then the first equation you should have written down, it's right over here, is the number of coins. That's how your first equation is going to be relating to. So the number of coins we have in total is 400. How much quarters do I have? I do not know. How much nickels do I have? I do not know. So leave them as two unknowns. Now we're going to talk about the price of each category or topic or whatever. So how much total dollars should I have? Or how much total dollar is in the coin jar that Johnny has? It is $48.40. How much quarters? How much do quarters cost? Well, they should cost 25 cents. So 0.25 Q. How much should nickels cost? Well, they should cost 0.05 M. Okay, 5 cents. So we set up our system over here. Now, once we have set up our system, we can solve for it. Try elimination out. If you did elimination, you would have multiplied by the first equation by -4. If you multiply by -4, do I have enough space to work with this? Yeah. I'd get negative Q minus 0.2N equals, what is -4 times that? 16, what is that? 16, 19. Let's just use a calculator real quick. 4 times, what is that amount? 48.4. 193. This is, yeah, 193.6. So this is negative 193.6. Over Q plus N equals 400. And now I can add them together. If I add them together, I get the Q, the quarters eliminate, and then the nickels, I get 0.8 nickels equals, if I add these together, it's the idea of subtracting. So I have, what is that, 200 and, I want to say, 70, 60, and then 5, 4, 246. And then your nickel amount should be, let's calculate that out. 246.40 divided by 0.8. 300. Did I do something wrong? I might have done something wrong. Let me see. Just real quick. My algebra might not be the best. Oops. This is negative plus 400. So yeah. And then divide this guy by, oops, 206.4. Divide that by 0.8. 258. So I gotta adjust that. 206.4. So let me fix that up real quick. And then nickels, we have 258. Well, if the nickels is 258, if I plug it back into my equation on here, then the quarter amount I have should be 142 quarters. So I can say that I have 142 quarters and 258 nickels. And of course, you can verify this if you want to. If they should add up to 400 coins in total, and if I actually calculate the price, 142 times 25 cents plus, you got that 258 plus 0.05. They should give me the exact same amount of dollars that the problem related to. So let's see, boom, boom, boom. So this does add up to 400, but why is it not? Did I put in the right one? 25.05. This is addition. I'm sorry about that. It's multiplication. Boom. $48.48. Perfect. So we're good to go on that word problem. So we're able to calculate these out. So, I also have a third type of word problem, but that could be, as a little, I guess, exercise you could try out on your own time. But I also want to talk about the next section. So now that we have worked with applications of these linear systems, and notice that the linear system has only been using two variables, two equations, we have to up our dimensions. Now, upping our dimensions means increasing the variables and increasing the number of equations we have. It depends. Sometimes you might have 5 equations, you might have 5 variables. You might have 5 equations, you might have 4 variables. You might have 6 variables with 5 equations. So you have to understand how to work with these problems. And this is when we get to the several variable system. So we can only imagine things in 3D, really. Nothing higher than third dimension. But the idea that we have with our problem, instead of working with lines, we're working with planes this time. We're going to treat our equation as a plane or a flat space. A space full of objects, but it's flat. That's how we're going to look at it. So, if we have exactly one solution for our system, then this is how it looks like. These 3 planes, they're intersecting at one common point. And that common point is over here. Just a singular point. That is very, very rare. Now, if we have infinite amount of solution for our systems, it connects at infinite amount of points. So instead of a single point, we have a line that is our solution. That is our solution, that entire purple line right there. All these planes connect at those points in particular. Now, this image is kind of inaccurate because, honestly, they miscolored this. So, in actuality, the blue part should be right here. This should be the blue as well. And then the green part should have been all of this right here. Just a slight coloring issue. I'm not going to blame them. Alright. Then, when you have no solution, that means there is no common intersection among the 3. If you look at the first picture, they are intersecting each other, but only one plane intersects the other. So not all 3 of them will connect at a singular point. If you look at the second image that we have, I have the one plane that intersects both of my other equations, but the 2 other equations are disjointed. And the last one, neither of the systems connects each other ever. In a sense, you want to think it like parallel. Okay, so these are the possible types of solution we can have. They behave the same way as working with lower dimensions. It's just, students might have trouble visualizing this. So now we go into some several variables. And in particular, we got to talk about a definition before we even get into anything. So the definition I want to introduce is a linear system. Not a linear system, a linear equation. We've already talked about linear system. Now we talk about linear equation because I'm increasing the dimensions on that. So a linear equation is of the form a1x1 plus a2x2 plus a3x3 plus ... all the way to an plus xn equals c. This is what a linear equation is in actuality. So what you'll observe is that our variables is x1, x2, x sub 3, x sub 4, all the way to x sub n. All right? We're not using x, y, and z to generalize this because, again, I can run out of letters in my alphabet. If there are 30 variables, I can't use my alphabet to list all of them. So I'm using these sub notations. All of the x sub 1, x sub I, or whatever, they're all going to be your variables in particular. Now notice that each of these variables has an exponent of only 1. None of them are being square root. None of them are being cubed. None of them are being multiplied by each other. Oops, this is a little inaccurate. This should have been an xn right here. But none of the xn's or x3, x4, they're not multiplying each other. The only thing they're multiplying is the a values. So what is their a values? These are our coefficients. They're actual constants. And then they're all equal to a constant. So that's what a linear equation is. Now we move on into some important stuff. So how do you solve these higher dimensional problems? Well, thankfully, there's a very nice little method we can actually use. This is called the Gaussian elimination. Oops, I spelled his name wrong. No disrespect to Gauss. You pronounce it Gauss because he's German, as a little heads up. Gaussian elimination. Or Gauss elimination. For short. So, there are 3 properties with Gaussian elimination, and it relates to elimination. The only difference is that some of them are slightly stronger, mainly because we want to work with higher dimensions. The other elimination we had, it is nice, it works out. It's just, it only works in a 2-dimensional case, so we need something to strengthen it. So the first property, now, it should follow the same thing as the regular elimination, but I'm going to make the assumption that we can always rearrange our variables. Even in Gauss elimination, we can always do that. So I'm not even going to put that in our properties or rules that we can do. We should already know that should be something we can do. The new thing that we're going to add is that I can interchange any position of equation with another. And I'm going to make a problem up just so you guys can see the idea. I can interchange any of them. Let's say I have 2x plus 3y plus 4z equals 1. And let's say I have x plus 2y plus z equals 3. And then I'm going to say I have negative 3y minus z equals 4. Let's say I have this system with 3 variables. We're going to work with 3 for now just to get the idea of it. But just know that I can't up the dimensions every single time and add the number of equations. So we're going with 3 equations by 3 variables, 3 by 3. And if I want to apply the Gaussian elimination rule 1, I can interchange any position of the equation with another. So if I wanted to swap the equation 1, equation 2, I can simply write, let's go from here to here. And you do need practice in showing your work. That is very important with these problems. So I'm going to say that, in particular, row 1 is going to swap with, which is arrow, row 2. That symbol means swap. So let me fix that up so you guys can see clearly. And then what happens is I get a new system, but it's still equivalent to the original system. So my system becomes x plus 2y plus z equals 3, and 2x plus 3y plus 4z equals 1, and negative 3y minus z equals 4. New system, but it's still equivalent to the old system. All I did was swap the rows, row 1 and row 2. That's what the R stands for. So I can write that as down. I can write swap rows. Now, Excuse my language, but what's going to happen from now on is that I might use the word row more often than I use equations. I'm going to refer to each equation as a row. And that's going to build into our next unit as well, or next section. So that's the first property we can do. Now the second property, if we look in our elimination, it says that we can add equations to one another. This one's a bit stronger. You can add any non-zero multiple of an equation to another. So it's more than just adding an equation. I'm putting that other part of elimination together. I'm saying that I can multiply one of the equations by a constant and then add that to the other equation. So let's go ahead and show what happens if I try this out over here. Let's suppose that I wanted to add, I don't know. Let's do it this way right here. So I'm going from this one right here into the next one. Let's say I wanted to do -2. I want to multiply the row 1 by -2, and I want to add it with row 1 and add it with row 2. But then I need to know what changes. I don't want to change row 1. I want to keep it that way. Let's say I want to keep it that way. Let's say I only want to change row 2. So I'm going to say whatever answer I get, I'm going to put it in row 2. So if I go over here and I'm saying that I'm multiplying this by -2, that means I'm going to add this guy by -2 times x plus 2y plus z equals 3. I'm going to add that to that guy, only on the second row. I'm not going to change the first row at all. And we'll talk about why I'm not changing it. So if I do that, I have x plus 2y. That's a weird y. 2y plus z equals 3. The first row does not change. The only row that changes is the second because I sent it to the second row. So if I add these two together, I get the x's cancel out. And then I get, distribute this. That's -4y plus positive 3y, which is -y. And then -2 times positive z is -2z plus 4z, which is positive 2z. And then -2 times 3 is -6. -6 plus 1 is -5. Minus z equals 4. This is my new system. I added the second row by -2 times the first row. So I scaled the first row by -2, but I added on to my row 2. Okay, I can choose to throw that resulting answer into the first row or the second row, but you need to tell me. When you show your work on the Chapter 5 test and on the final, you need to tell me what's exactly happening, because some students are going to have 20 different systems. Some students might only have 2 systems. Some students might have done something like swap the rows, and the other students might have gone into this vortex. And I don't mind it either. I just need to see what's happening. All right, so that's the second property. And the third property, I already kind of hinted at it, is the same thing as elimination, is that we can scale any row by a constant. I should say non-zero constant, but I think by now we should know. I should just say it. Non-zero. Please don't multiply it by 0. All right, so what that means is that I can multiply any row by a single constant. Let's say on row 2, I want to multiply this by -1. So or let's say row 3 by -3. So I want to do -1/3 of row 3. You can multiply by anything. I'm going to choose to multiply by -1/3. If I do that, I have x plus 2y plus z equals 3. -y plus 2z equals -5. And then I have y plus 1/3 z equals -4/3. -4/3. Boom. This is my new system over here. So you're able to do that. You're able to just scale it by any specific constant you want. It could be negative, it could be positive, it could be a fraction, which means division, it could be any of that. So I've shown you how to swap rows. I've shown you how to add it with another row, any multiple of another row, and I've also showed you how to scale it. That is all of Gauss elimination. These tools help us solve any system we want, any linear system we want in higher dimension. It doesn't matter if I have 20 equations, 20 variables, I am able to solve it. Now, if it has a solution, that's a different story. So now, let's talk about an example that we could have. How did we even use this? Example. Let's suppose I have, let's see. What size is this? Let's make it larger. X minus 2y minus z equals 1. Negative x plus 3y plus 3z equals 4. And the last one is 2x minus 3y plus z equals 10. Let's say I have this system and I want to solve the system. Well, it's not like the other system anymore, because the other system, you can probably look at it and find a solution. This, you cannot do that at all. It's gotten to the point where I can't just make up problems just like that anymore, where our problems are always chosen in the book now. So in this problem right here, it's not easy to find a solution. However, let's suppose that I did some Gaussian elimination. Gauss elimination. I'm not going to tell you what exactly I did. We're going to figure that out later on. But let's suppose I did a lot of Gaussian elimination. And then eventually my resulting solution looks like, or system looks like this. X minus 2y minus z equals 1. Y plus 2z equals 5. And z equals 3. So I turned the first system into this new equivalent system using Gaussian elimination. Now, the question is, why, and what do you observe about this? I'll leave it paused. Go ahead and think about some observation about this second system. All right, so if you made some observation, you notice that this says z equals 3, which means if I plug it into over here, I can solve for y, and if I plug those two in here, I can solve for x. So I can find a solution. That's nice. But there's other observations you can make. Notice that in this system right here, there's a lot of empty space. Right here in particular. On this diagonal. There's an empty space. We have, in particular, a triangle right here. We also have a triangle right here if you think about it. This is called triangular form. Now, what's also neat about this is that, hey, if you look at our variables, the leading variable, we started with x, we started with y, we started with z. Some of the other variables got deleted, but it's x, y, and z. The first variable is in the first row. The second variable starts off in the second row. The third variable starts off in the third row. That's another observation we can make. The final observation that we can make that helps us out is that x, y, and z, each of these variables has a leading coefficient of 1. So we're going to say that triangular form. This is nice. Triangular form. Now, if you do your WebAssign, well, your WebAssign doesn't really require to have leading coefficient of 1. But I'm going to say leading coefficient of 1 just for practice, and it builds you into the next section. Triangular form requires the nth variable to lead on the nth equation. And leading coefficient is 1. So let's jam pack everything together. I'm saying the nth variable has to be the leading variable on the nth equation. Well, let's think about it. The second variable in my problem, well, the second variable is y. Notice that it leads on the second equation. My third variable is z. On the third equation, it is the leading variable on the third equation. My first variable is x. That is my leading variable on the first row. So that is very important. Your leading variable will be leading on the nth row or equation. If I was on the fifth equation, I'd want to lead with the fifth variable. That means I need to delete every other variables before that variable. Notice that there is no x here at all. There's no x. There's no x and y here. They got deleted. So you have to do some elimination. Eliminate the ones necessary. This is a very organized way of solving multi-dimensional linear systems. All right, so now we have this idea, triangular form. Oops, I don't know why that erased. Boom. Now we can work on some more examples, some practice. Or we can go with this one, and let's see if we can actually figure it out. So let me go rewrite that out for us. So we have x minus 2y minus z equals 1. Negative x plus 3y plus 3z equals 4. And 2x minus 3y plus z equals 10. This system right here. If I look at this system, we have to ask ourselves, let's look at the first row in particular. Is the first row in particular nice or not? And what I mean by nice, does it follow the triangular form rule? Is the leading coefficient 1? And does the first variable lead the first equation? Well, the first variable is x. Is the leading variable x in the first equation? Yes. It has the coefficient of 1, so we're good on that. So we don't need to change the first row at all. Now, let's look at the second row. The second row should lead with the variable y. Does it lead with y? No, it has a negative x. I need to delete this guy right here. And I also need to delete this guy. So I have to do that right now. Now, you can also swap rows and everything, but swapping rows doesn't help us out at the moment. If this was leading with y on the third row, I could swap it to the second row and then skip a lot of steps. But right now, swapping rows does not help. I need to get rid of negative x somehow. Somehow I need to get rid of negative x. How can I get rid of negative x? Well, what I can do here is I can add row 1 plus row 2. If I do that because I need to get rid of negative x, which means I need to add a positive x. And notice row 1 has a positive x. So if I add those two together, the x's should be gone. So if I add them together, I get the first row stays the exact same. I didn't change anything. I'm going to put this in row 2. The second row now becomes, well, if I add them together, I have y plus 2z equals 5. And the third row, nothing changed with that. So this is 2x minus 3y plus z equals 10. This is our new system. It's still equivalent because we're only using these properties. Great. Now, if we look at our second row, is the y the leading variable? Yes. Now, does it has a leading coefficient of 1? Yes. So we're good to go. We are done messing with row 1, and we are done messing with row 2. Now we got to work with row 3. Row 3, we need to get rid of this entire guy. Oops, let me use a different color. We need to get rid of this entire guy. We also need to get rid of this entire guy. I have to. So if I do that, to get rid of x, 2x, what can I do? Can I add it with the second row? No. The reason why, you need to add a negative 2x in, but if I try to add it with the second row, it doesn't have an x at all. So there's no way I can delete that 2x ever. I need to add it with the first row. If I add it with the first row, I can somehow delete it, but I have to multiply the first row by some constant to get rid of 2x. I need negative 2x, so I'm going to multiply the first row by negative 2 times row 1 plus row 2. I'm going to set, oops, not row 2, row 3. And I'm going to send that to row 3. If I do that, my x's should be deleted. So let's go ahead and do that. If I do that, I get x minus 2y minus z equals 1. That still stays the exact same. And then you have y plus 2z equals 5. Now I'm multiplying this first row by, or let me write it over here. I'm adding the third row again by 2 times. So plus 2 times negative 2, I'm sorry. X minus 2y minus z equals 1. I gotta add them together. So you gotta do some mental math in here. Or you can write it out. I do not mind. If I add them together, the x's are deleted because it's negative 2 plus 2x. They're gone. And then if I do negative 3y plus 4y, that's just positive y. And then if I do z plus positive 2z, that's 3z. And then 10 plus negative 2, which is 8. That's after I perform this operation right here. Great. Now on our third equation, the x's are deleted. We're happy. But remember, the leading variable should be z. So I need to get rid of that y right now. Let's get rid of that y. How can I get rid of that y? Some of you might have said, we're going to multiply the first row by 1/2, and then we can add them two together. That will delete the y. Oops, sorry. That will delete the y, but the problem with adding it by row 1 is that I'm going to gain an x. I've already deleted the x. Why do I want the same variable again? No, I only want z to be available. So I have to add it by some multiple of row 2, because the row 2 does not have any x's at all. It only has y's and z's. So what I'm going to do is I'm going to do negative of row 2 plus row 3. That should get me the y's deleted. If I multiply the second row by negative 1, I get negative y plus positive y, and they're gone. So I get x minus 2y minus z equals 1. Get in the habit of writing all these systems out. If you do not, you will make mistakes. Plus 2z equals 5. And the last one, the y's are deleted. The y's are deleted. I'm adding this by, what is that? Negative 1 times y plus 2z equals 5. And then if I do that, that should give me, the y's cancel out. And then I get z right here by itself equals 3. This is my new system. Now, if you look, this system, the z is good to go. We're good to go on that. If I didn't do any mistakes, the z has no leading coefficient, so we're happy. Now, look into our triangle form. They're the exact same, so we know we're good. Now, I also expect you to be able to find a solution with this. The solution is going to be it's going to be an ordered triple, not an ordered pair, ordered triple. We're going to have 3 for the z value. We need to figure out the other values. So let's go ahead and figure those out. If I substitute z in, this becomes y plus 2 times 3 equals 5, which is y plus 6 equals 5. Y is equal to negative 1. Negative 1 for the y component. And the last variable, I have to plug in x minus 2 times negative 1 minus 3 equals 1. Then if I calculate this out, what happens if I calculate this out? This is x plus 2 minus 3 minus 1 equals 1. So x is equal to 2. This is our solution right here. 2 comma negative 1 comma 3. Let's take a look at that graphically. Now, I can't use Desmos because I don't think Desmos use 3D calculating, but let's see, 3D calculator. Let's look at GeoGebra. GeoGebra is a very good site to just visualize this. It doesn't do the calculations for you, but you can visualize a lot of stuff together. So our equation was x minus 2y minus z equals 1. And then the second equation was negative x plus 3y. This is the original system. Equals 4. And then the final one is 2x minus 3y plus z equals 10. Now let me change the opacity and the color. Let's do this as this opacity here. Let's do purple. Boom. And then this settings right here, I want to change this color into, let's do red, opacity all the way to max. The settings, let's do this blue, opacity all the way to the max. Alright, and then I can close this out now. This is our planes that are intersecting. Do you see they have multiple different intersections? However, I want the intersection where all three of them connect. Well, it turns out all three of them connect exactly at 2, comma, negative 1, comma 3. Boom. That is where the intersection of all three planes intersect one another. This is on the X, Y, and Z axis. That blue line, that vertical blue line right here, that's our Z axis. Your X and Y are the green and red. So this is what our solution set looks like. Boom, it's that singular point amongst these three planes. And you can see how rare it is to actually have a solution in a system with several variables. So we are lucky about it. Later on, if you guys ever move into a higher level course, you'll realize that, hey, I might not have a solution, but I can find a solution that is the closest possible solution. Or I can find a value that is the closest possible solution to the supposed solution, even if it doesn't exist. That's a very powerful thing. All right, so going back, let's do another practice just to make sure we're on point with this. Let's do, I want to do that. Where's it at? In particular, I want you guys to try this one out. X minus y minus z equals 4, negative x plus y minus 2z equals 5, and 2y plus z equals negative 1. This system right here. If I'm working with, that's a weird curly braces. I'm actually disappointed with myself on that one. And that one too. Boom. This system right here. If I'm working with this system, go ahead and take some time to try to solve it out. I'll leave it pause for about 5 seconds, and then I'll come back. You guys can pause it for as long as you like and try to work it out. Alright, so if you try to actually solve it out, you'll notice that the first row leads with the variable x and has a leading coefficient of 1. That is nice. We are okay with that, so we don't need to mess with it. The second row does not have a leading variable of y. However, some of you guys might have seen this. This third row does lead with y. So what we can do instead is we can swap the rows. So I'm going to do row 3 swaps with row 2. If I swap them together, I get x minus y minus z equals 4, 2y plus z equals negative 1, and I get negative x plus y minus 2z equals 5. Boom. So now I've already got rid of the x term by swapping the rows. It's very nice in that case. If one of the rows have already lost that term, go ahead and swap it. It might be easier. It might save you a lot of work. Now, going forward, I noticed that I didn't really get rid of the leading coefficient, so I have to get rid of that. The best way to get rid of leading coefficient is to scale it. So I'm going to scale row 2 by 1/2. If I scale it by 1/2, I have x minus y minus z equals 4. And then I have y plus 1/2 z equals negative 1/2. And then the third equation is going to be negative x plus y minus 2z equals 5. Boom. I've scaled it down. So the second equation, we're good to go. We're happy about it, thankfully. The third equation, it has an x, it has a y. I need to delete these guys. Well, to delete these guys, delete the x, I have to use an equation with an x because I have to add it by x. So I can add row 1 plus row 3, and I'm going to send that to row 3. If I do that, I have x minus y minus z equals 4. The second equation stays the exact same as well. y plus 1/2 z equals negative 1/2. And in the third equation now, the x's are deleted. X plus negative x, that's gone. Negative y plus positive y, that's also gone. Then negative z plus negative 2z, that's negative 3z. So we were very lucky that the y's got deleted as well. Equals 9. I'm already done. I'm almost done. Not already, but I'm almost done. Now I just need to scale this. This would technically be in triangular form, by the way. But my definition of triangular form, I want to get rid of the coefficients as well. Again, your WebAssign might treat this as triangular form, which you should understand. All right, so I'm going to simplify this even more. I'm going to divide or multiply, scale the third equation by negative 1/3. Notice I'm not doing division. It is treated like division, but I haven't talked about subtraction or division. And the reason why is because when we're working with these problems, you can lose track of how to add a negative, subtract a negative, all of that. It's very common that students, when they try to subtract or divide, they mess up. X minus y minus z equals 4. Y plus 1/2 z equals negative 1/2. Then I have z is equal to negative 3. And then my solution set, you can calculate it out. It should be negative 3. If I plug in negative 3 to the second equation, I have y plus 1/2 times negative 3 equals negative 1/2. That's y is equal to negative 3/2 equals negative 1/2. It's not an equal, so this is a plus. Keep messing that up. Now I'm going to add 3/2 to both sides, so I get y is equal to 2/2. Y is equal to 1. That worked out nicely, even though it was a fraction. And if I plug it into the final one, that's x minus 1 minus negative 3 equals 4. X, what is that? Plus 2 equals 4. X is equal to 2. This is my solution. Boom. So we're okay with solving it if it has one solution in particular. Let's move on to another one. What happens this time if I have a different problem that's not exactly one solution? So let's work with one with an infinite solution in particular. X minus y plus 5z equals negative 2. 2x plus y plus 4z equals positive 2. And 2x plus 4y minus 2z equals to 8. If I wanted to solve this one out. Now, let's go ahead and just try to solve this out together. So if I noticed already that the first equation is actually good to go. Our first equation is nice. Let me move that. Our first equation is very nice. The leading variable is x. The leading coefficient of x is 1. So it is already in triangular form. The second equation is what we need to fix. So I'm actually going to multiply this by, we're going to add it by negative 2 of row 1 plus row 2. Oops, I wrote that terribly. I'm going to send it to row 2. You need to tell me where you sent it. So if I do that, I get, I don't know if I have enough space, but I'll do it over here, down here. I have x minus y plus 5z equals negative 2. Now I'm going to add this with negative 2 times row 1. And I write it right here just so I can see what's happening. Okay? So if I add them together, the x's are gone, thankfully. The y's, I have negative 2 times negative y, which is positive 2y plus y. That's 3y. Negative 2 times 5z, that's negative 5z plus 4z, or it's negative 10z, plus 4z, that is negative 6z, equals negative 4 plus 2 is negative 2. And the final part is just 2x plus 4y minus 2z equals 8. Now what some of you guys might have done, you guys might have added negative 1 of row 2 plus row 3, and then the x's are deleted. Some of you guys did that route. That is also a route you could have taken. But I'm going to do my route. And that's why I need to show your work, because everybody's going to do it differently. If I see everybody doing every single problem in the same way, I'm going to suspect something. I'll just be honest. These problems are not as, I guess they're very generous on the number of ways you can solve them. So over here, now the second equation is almost good to go. I just need to multiply that by negative 1/3 of R2. So I have x minus y plus 5z equals negative 2. Then I have y, what is that? Plus 2z equals, wait a minute, something went wrong. I did negative 2 times negative 2, that's positive 4, plus 2, that's 6. This should have been a 6. Apologize for that, that should have been a 6. Plus 2. And then this is all over, or this is going to be 2x plus 4y minus 2z equals 8. So first equation is good. Second equation is good now. The leading variable is y. And on the second row, the coefficient is 1. Now I just got to do with the last row. Well, the last row, I got to add negative 2 of row 1 plus row 3. Send that to row 3. Then I get x minus y plus 5z equals negative 2. Y plus 2z equals 2. And if I add that last row together, what should I get? Let's see. So that's the x's are gone. Then I got positive 2y plus 4y. That's 6y. 6y. And then negative 2 times 5z. That's negative 10z plus negative 2. That is 8z equals, and then negative 2 times negative 2, that's positive 4 plus 8 is 12. I want to see if I did everything right. This should have been a minus 12z right here. Because negative 2 times 5z, that's negative 10z, plus negative 2z, that's negative 12z. Yep. Now, I got to get rid of the y's. To get rid of the y's, I have to add this by negative 6 of row 2 plus row 3. I'm going to send it to row 3. If I do that, oops, I'm running out of space. First equation stays the exact same, of course. Minus y plus 5z equals negative 2. Then I have y plus 2z equals positive 2. And then the last part I have, let me just see if I wrote down the systems correctly. Yep, we're good to go. If I add them together, the y's are deleted. The z's are deleted. So I get 0 equals 0. What does that mean? Well, 0 equals 0 is a true statement. Now, if you notice, we have a spot for our x, our y, but then our z says 0 equals 0. That's our third row represents our z, our third variable. And we have 0 equals 0. That's a problem. This means that z is free. It's a free variable. Z can be any number you want. Any number you want. So I'm going to let z to be equal to any number. I'm going to call it t. T can be any number you want it to be. Any number possible. Now, just because the z variable is free, does that mean I have all solution possible? No. I can have any z value possible, but y and x, do you guys know they have a z variable? That means y and x will depend on our variable t. This is why we call infinite solutions systems with infinite solution a dependent system. They're dependent because they depend on whatever value z I put in. So if I plug in t and try to solve for y, so I see what I did wrong. So this should have been positive 1/3. So that's where I make a mistake. If I did positive 1/3 of it, this becomes y minus, so I apologize for that. Y minus, or y minus 2z, and then this should be positive 2. Yep. So y minus, so I made an error, boom, 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 minus 2z minus 2, and the last part is y minus 2z, And then this should have been y minus 2z minus 2. Now let me erase all this. Then I get y is equal to negative 2 plus 2t. There we go. Now I have the right value. So now I can fix that up. I have negative 2 plus, boom, boom, boom. Let me write this better. Negative 2 plus 2t. If I solve for x, I have x minus negative 2 plus 2t plus 5t equals negative 2. If I distribute this over, I get x plus 2 minus 2t plus 5t equals negative 2. X is, if I combine these, this is plus 2 plus 3t equals negative 2. So x is equal to negative 3t. Ah, this was supposed to be a positive 2. Yeah, this is supposed to be positive 2. Let me fix that up. Yep, boom, boom, boom. Positive 2. Positive 2. So this is positive 2. This is positive 2. And then this becomes negative 2 over here. And then afterwards, then they get deleted and we get x equals to negative 3t. So then the final part is x equals negative 3t. So this is our solution set. And if we would write it down as an ordered pair in terms of t, our solution is going to be exactly negative 3t comma negative 2 plus 2t comma t. And I want to express it in t's because I don't want to use x, y, and z as my coordinates. They are positions. So I need to know what's in the x position, the y position, and the z position. And I have to use a different variable to express that what values they could be. So this is an infinite amount of solution. It's not more than one because if I choose t to be equal to 0, my coordinates becomes 0, comma, negative 2, comma, 0. If my t was 1, then I have negative 3, comma, 0, comma, 1. So it does depend on your t value in this case. Sometimes not all of your positions will depend on t. One of them might be fixed. They might be frozen as a specific number. And the other ones could depend on t. So it depends on the problem that you have. In this case, all of the position will depend on z, which depends on t. Z is my free variable. So that is how you do these problems. I apologize for all the mistakes, but that lets you know how many mistakes can happen in these problems. You have to be very careful and look out for those when you're doing these problems. So write big and try to do your work slowly so you don't make as much mistakes. And if you do make mistakes, you should be able to catch it on like I did. And that's it for today. I will catch you guys later. Take care.